Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of particle physics with the course code PHY 452, we are at the lecture number 13 and the topic is fundamental interactions. As we know that in the standard model of particle physics, we have two major components. The first component deals with the matter content, that is the number of fundamental elementary particles we have, and the second component deals with the forces which these particles exert on each other. We have learned about the matter content of the standard model before. In today's lecture, we are going to talk about the four fundamental forces in the standard model. First of all, there are four forces in the nature which these particles exert on each other. We don't know that why this number is 4, but the physicists in the past have tried hard to reduce this number by combining different kinds of forces into each other. We were partially successful as some of the forces were combined and the number of fundamental forces reduced, but we were not successful in bringing it to the number 1. That is, we have only one force in the nature, which all other forces originate from that force. But at low energies and in the standard model, we still have these four forces which are independent of each other. We list these four forces depending on their relative strengths. In order to give you the listing of the forces depending on their strengths, we have to first understand what do we mean by strength of a force. For this, consider that we have two particles, probably you can think of them as identical, and also consider that there are two forces acting between them. Let's say the first force is F1, which is acting between these two particles, and there is another force F2 which is also acting between these two particles. Now we want to know which force is stronger than the other. Now if F1 acts faster, that is, if it acts in 1 second between these two particles, and F2 takes time when the particle 1 affects the particle 2 via F2 is, let's say, 2 seconds, then we say that F1 is stronger than F2. So if it takes less time for any force to be exerted between the two particles, we say that it is stronger. In our case of four forces, we know that some of the forces is stronger than others. If we make the listing depending on this relative strength, then the strongest force is strong nuclear force. It is the strongest of all the forces we know. The second number is electromagnetic force, and the third number is weak nuclear force, and the fourth number is gravitational force. I will in future slides in detail explain that what is their strength and what is the range of these forces. The second property, as I have already mentioned, is the range of these forces. By the range, we mean that if we have two particles and they are separated by some distance, let's say r, then at how much separation force is still effective. So if the force is effective at smaller distances, we say that it is a short range force. But if force is even effective at infinite distances, we say that the range of the force is infinite. So depending on the range, if we mention the ranges of all the four forces, then the strong nuclear force is in fact short range force, because it is only effective inside the nucleus. On the other hand, electromagnetic force is infinite force. It has infinite range. So if you have a particle which is situated at the earth and another electron, for example, the same particle on the moon, still they will have some interaction between them, electromagnetic interaction. And then we have a weak nuclear force, which is also a short range, because it was initially almost thought of to be a contact force, which means that it is in operation when two particles are in contact. But now we know that although it is very, very short range, but still it has some at separation distance it is effective. And the last force is gravitational force. So gravitational force is also infinite range, which means that if two particles are separated by infinite distance, for example, if one particle is sitting at the one end of the universe and the other particle is sitting at the other end of the universe, maybe very feeble, very small force is there, but still the gravitational force will be present between these two particles. The next property which we want to explain is the mediators. In quantum mechanical version of the forces are between two particles are transmitted with the help of mediators. The concept is that first particle exits some kind of or emits some kind of particle, another particle, and that particle then travels and absorbed or reflected by the second particle. By this way they are connected and exert force on each other. Roughly speaking, in order to make it more concise, we can say that there are some sorts of messenger particles which take message from one particle of being repelled or it being attracted and take it to the another particle, and when this message is received by the other particle, then it acts accordingly. By this way the force is transmitted between two particles. So now we should have a messenger for all forces, and we have messengers for all forces, and they vary in number and type. For example, the strong nuclear force has messengers named gluons. In coming lectures we will see in detail that what are gluons and how they mediate force between different kind of quarks. The strong nuclear force is mediated between different kind of quarks. And the second force is electromagnetic force. Its mediator is photon. By the way, the number of gluons we have is 8 and we have only one photon. There are technical reasons for it, because in strong nuclear force case we have gauge group SU3 and it has 8 generators, therefore we have 8 gluons. In the electromagnetic force we have gauge group U1 and it has only one generator, that's why we have only one photon. The third force is weak nuclear force. It is described by Glashow-Weinberg-Salam model, and there we have intermediate vector bosons W plus, W minus and Z naught. They are called intermediate vector bosons, and they are 3 in number because the gauge group for weak nuclear force is SU2 and it has 3 generators. The last force is gravitational force and its mediator is graviton. It is important to note that this graviton is still not detected because gravity is also not quantized. So these 3 forces are quantum mechanical. These are all quantum mechanical, but the gravity is still classical theory, and therefore its mediator, a hypothetical particle graviton of spin 2, is still at large and is not detected. So it is not confirmed, but still to make the story complete we say that gravitational force has a mediator graviton. So we have now mediators or messenger particles for all our 4 forces. Now I will go one by one to each force and explain its different properties in order to give you the exact strength, ranges and all other properties and the theories which describes them. So I will start with a strong nuclear force, that is strong interaction. In strong interaction, the relative strength of the strong force is 10 to the power 38. That is a number which is relative to other forces. You will see the other forces will decrease down because this is the strongest force we have. So if you have 2 particles which can feel all the 4 forces, then strong nuclear force will be the first force to act between them. So it's a faster one and therefore stronger. The second thing is the range. As we already mentioned that it is the short range force, so order of 10 to the power minus 15 meter. So it is only active inside the nucleus. Outside the nucleus, if there are protons which are at the distance separated more than 10 to the power minus 15 meter, then they will not be affected by the strong nuclear force. So this is a short range force. The third is mediators, as already mentioned, that there are 8 gluons. So these are the Young-Mills theories which have or gauge theories which have gauge groups which describe them. So gauge group for the strong nuclear interaction is SU3, and that has 8 generators. Because of this, it has 8 gluons. So these 8 gluons actually mediate the force between quarks and protons and neutrons. So in principle, a proton is made of 3 quarks, similarly a neutron, and these quarks force between them, actually it is called color force, is mediated by the 8 gluons. So this is the reason the SU2, the gauge group is SU3 for it, and it has 8 generators. And this is the reason that we have 8 gluons over here. We will explain these things in more detail in coming lectures. The next thing is the long distance behavior. The long distance behavior means when the quarks are at extreme distances, then how the force is behaving. It is behaving like R to the power 1. It is important to note that the recent developments, not very recent, but there are developments where we know that when these quarks come very close to each other, they are almost free and feel no force. This is called asymptotic freedom. But when they are at large distances, the force is acting like 1 or like R. And the last thing is the theory which describes the strong interaction. The theory is called quantum chromodynamics, because these quarks carry an extra charge called color, and it comes in 3 types, that is red, blue and green. And when they move, they emit gluons, they are mediators, and they also carry a color, and then they interact in very complicated way. And all these interactions are described by dynamics of these color charges. That's why it is called quantum chromodynamics. That in detail explains all the phenomena included in the strong interaction. But over here, I want to give only the important facts about this strong interaction. In future lectures, we will, or in QCD lectures, you can learn that how these 8 gluons arise, how the strength arise from equations, and also the basics of QCD. But at the moment, you can just remember these facts in order to get yourself acquainted with these forces. The next force in the order of decreasing strength is electromagnetic interaction. It is very well known to us. It's very common. The daily life routine, you can see that all the things are bounded because of the electromagnetic interactions. Its relative strength is 10 to the power 36, so it's way weaker than the strong nuclear force, and its range is infinite. As I said, that if there is an electron at the one end of the universe and another electron at the another end of the universe, they will still be interacting via electromagnetic force. And the mediators are photon, gamma, only one mediator, because it is governed by U1 gauge group, and it has only one generator. So this one generator corresponds to a one mediator, that is photon. So 2 electrons or 2 charged particles mediate or emit or absorb a photon between them in order to exert electromagnetic force on each other. And its long distance behavior, as it's well known to everyone, is 1 over r square. So it's inverse square force. In Coulomb's law, you see that 1 over r square coming, this factor coming up there. This is its long distance behavior. And the theory which describes it is the quantum electrodynamic. Actually, it is the quantum version of the classical electrodynamics, where it was the first successful theory developed quantum mechanically. In my next lecture, you will find out details on quantum electrodynamics, where I will give all the processes and Feynman diagrams for calculating the electromagnetic interaction between two charged particles. So next force is the weak interaction. This weak interaction is responsible for the beta decay. If you remember that inside nucleus the neutron goes into a proton plus some electron, some beta particle and some neutrinos. So in this interaction, this neutron decaying into proton and emitting some kind of electron is called beta decay, and the Fermi theory actually explained that, but later on a more complicated theory for this emerged. But we know that weak interaction is weaker than the electromagnetic force, and its strength is almost about 10 to the power 25 on the order of in the relative sense, and its range is 10 to the power minus 18 meters. So it is almost a contact force, but it's not exactly the contact force, and there is some separation. So it at this distance this force is effective. It has three mediators, W plus, W minus and Z naught. As I said, after the Fermi theory, Salam, Weinberg and Glashow given their own model, and in this model they explain in detail the weak interaction. Actually these three phases were able to combine the weak nuclear force with the electromagnetic force, and this was the first instance of combining the fundamental forces together in the modern era. And their theory was called an electroweak theory, where one mediator photon was somehow combined with these three mediators. And in Salam, Weinberg, Glashow model, they have exactly calculated the masses, and later on in 1983 these three particles were observed at CERN, and all these three were given a Nobel Prize in 1979, sorry. And its long distance behavior is somehow 1 over r. It is not exactly 1 over r because it depends upon the mass of the mediator, but still roughly speaking it behaves like 1 over r at extreme distance of its range. And the theory, as I said, is electroweak theory, and this theory is also quantum mechanical and quite successful in explaining the weak interaction. The next force we have is the gravitational force, which is still not quantized. As I already mentioned, it is quantum version of gravity is still not experimentally verified, although some candidates are there for it. For example, string theory has a quantum mechanical version of gravitation, but it is not confirmed or experimentally verified. Its strength is 1, as we set it equal to 1. That's why as compared to other forces, it is the weakest of the forces, gravity, but still a very important force in our lives. And its range is again infinite. If two particles are separated by infinite distances, still there will be some gravitational force acting between them. And the mediators, hypothetical gluon, it's a spin 2 particle, but as you know that it's still not quantized, so we don't know that whether there will be a gluon or not, but it is a hypothetical particle. The long distance behavior by Newton law, 1 over r square behavior, it comes in the Newton's law of gravitation. So at long distances it behaves like this. And the theory for the classical gravitational force is general relativity given by Einstein, and it is very wonderful theory, and it is in terms of the curvatures of the space-time, gravity is explained, but unfortunately the quantum version of this general relativity is still not known or not experimentally verified, although there are candidates for it. So we know that this general relativity explains at least classically the gravitational force. So in this lecture I tried to give you the overview and introduction of all the four forces and their different properties, and wanted to give you the flavor of that how these forces are different from each other. In our coming lectures I will be explaining in detail the technically different kind of these forces. I will start with the first force, that is quantum electrodynamics, and will go on to build upon it the other quantum versions of theories, for example quantum chromodynamics. With this I thank you all.